It's really a problem. I really talk in the faculty meeting. It is really a problem. But so far there is no solution. And I have 2 students, but they have to work really hard. I can't write their thesis myself, so that's some problem. But if they come work hard during summer, they may finish the degree program. Okay, this is the input noise problem, still noise, how to handle the noise. And noise passes through the system here. Another case we have done quite a bit for noise does not pass through the system. Then we have system parameters such as frequency response function, system frequency response function. Important factor is all spectra like autospectra, cross spectra, coherence function, and what's good for it. That's what I try to explain. And today's lectures and next week's lecture is really regarding the noise, how to handle the noise. So first we're going to look at the noise which passes through the system. So over here, this is M, input noise. X is main signal. This is like a transducer to pick up the input. And this is a system parameter, H. And this is output response, okay? So then this case is similar. We have done this. The noise does not go through the system. So first, the noise passes through the system. It's really 100% identical approach is what I'm showing. Very easy to get the final expression in terms of the spectra. So here, write as Y is what? Fourier transform of Y. So I put here, sometimes I put this as a reminder, then I drop that, okay? It's telling you everything is a finite. Finite means there is an error involved. So that's what we are working on. In finite element, you're involved in error. So you have to really test out the convergence criteria, whether you can handle or minimize the error or not. So then multiply Y is H times X plus M. It's all frequency domain. By looking at this very clear. Then X star. Star means conjugate Y. Then X star X, X absolute square, plus X star M. Then now, at this point, you can throw into the spectra domain. So this is GXY, and H stays as is. This is a GXX, this is a GXM. But GXM is, if M is independent, you can just drop that terms. So H, if it's not correlated, if X and M is correlated, then you have to leave as is. Independent, you can drop that. So just carry as is. So system response, frequency response, or transfer function is GXY over GXX plus GXM. True frequency, the response function. Not measured response function. Measured response function is hxy. So x you can tap in, y you can tap in, then you can compute the hxy. This is a measured the frequency response, gxy over gxx. Then you can just divide these two equations. Then hxy can be expressed as h 1 plus gxm over gxx. So as I indicated as a reminder, h is affected because hxy and h has relations, and hxy is affected by gxm, and h is affected by gxm. So whenever noise is affected, then you can use the word, that's the easiest way to remember, saying that this is a biased estimate. Okay? And measured frequency response function, there is a GXM. Independent noise, then that term drops off, and H and HXY are the same. So this case is we have handled this before, but here the parameter we are dealing are different. So here is a system, here is input. It's really pure input. This is a noise. But this case I said here GMU and GMY. So M is kind of a correlated noise. There is no relation between this guy and the U or Y, okay? Because it stays in input side. So X is equal to U plus M. X is equal to U plus M. This is the measured, X is measured input from the transducer. I think when you involved last Monday and Wednesday for measurement, I hope you learned the measurement data, and I hope he showed the accelerometer. You saw all that, but that's a very typical size. But there is a miniature size, even much smaller, and pick up the high frequency response also. So you saw, I'm pretty sure you have done the measurement of frequency response function GXX, GYY, GXY, magnitude, phase, and all that. But I hope you really spend at least 2 hours, total maybe 2 to 3 hours to see that. So that could give you some better understanding. So GMU, GMY is equal to 0, and so X is equal to U plus M. In frequency domain, it is capital X, U plus M. Then at this stage, you can throw into the spectral domain. So GXX, GUU plus GMM. What happened to the GUU, GMM? What about the GXM, GMU? It's 0, uncorrelated noise. So H is GUY over GUU. Can you, by looking at it, can you tell right away? Because it's straight from here to here. Okay. And the GXY, by the measurement, all you have is X transducer output and Y transducer output. This is always true as a measured frequency response function. This is true from the diagram. So over there, GXY is equal to GUY dropping GMY. Then this equation is, you just divide these two equations. Then the result comes as HXY is a function of the GMM, input noise in there. So this is what the relation. So H here is showing up there. And my note, I always claim equation-wise, I include most of the equations. I put the derivation in there. Then you can easily look through. And I didn't skip the derivation often. But here some I skipped it. When I skipped it, I have done it before. So this GXY is equal to GY is equal to H times GUU. Then star, you have to put the star here. This is complex, this is real. And can you remember the derivation I have done? The GXY star is equal to GYX. Only Friday I did. Happened to be the Friday. So I hope other students should pick up and go through this equivalency in the deriving the equations and all that. This is not difficult to derive it, but have to know. Otherwise, they will have a problem. H stars and all that. Then HGYY relation between this guy end up to be H times, you can write as a GYX, and showing this is measurable, this is measurable. Is this measurable? Measurable. Two stations you are dealing, X and Y. You can just flip it. And H can be calculated, of course. And you can compute the GUU. So when you have, it's always good to draw the diagram and find out which is measurable, which is not measurable. Some parameters are computable based on the measurable quantity. That you have to really separate. Otherwise, you can't solve the problem. So that's what this problem set and next problem set, feedback control. That's what a very good problem to practice. It's more complicated, but doesn't mean anything. It's input side, output side. There is the noise in input and output. That's what this is. But this time you have to really pay a little bit attention. This is kind of the one of most complex situation, as you will see. And the diagram is concerned, we learned the situation in output, we learned the situation in the input, we just combined that two together and assume here the difference is M and N are correlated, similar source or same source, noise source. And the gamma mn square, coherence function for the noise, same, ranges between 0 and 1. One input side, of course, we assume the m is not passing through the system. Another case you can think of is input. This can be passed through the system and vice versa. Then first define the input noise to signal ratio. If you if you look at the box downstairs, as you look at the function generators and all that, there is a signal to noise to signal ratio. I don't think you really practice that a little bit. You can contaminate the signal, like a sine signal, with a 10% noise or 20% noise. Okay? Then I think you have done that. So then when you take the probability model, probability density function, you saw how the noise is affected. Noise is affecting the sinusoidal based probability density function. You have done that, right? If you just draw pure sinusoidal function and take a probability density function, it's going to be straight up and down and down. That's what the pure, right? So if you contaminate 20% noise in there, then things are changing slowly, lesser down than that. If you really put 100% noise, then real signal is gone. It's all just hide behind. Then you have a normal the density function or Gaussian density function. So that's what the noise to signal ratio. We have a noise in input side. We have a noise in output side. So of course, input noise to signal ratio and output noise to signal ratio. UU is a pure, right? UU, and VV is in output side, and input noise, output noise. I just defined as the alpha and the beta. Of course, this is a function of the natural frequency. I'm sorry, it's just frequency, not the natural frequency. XX, UU plus MM, clear. There is no cross term. There is no GUM because it's not correlated in the input side. Same thing in the output side. Then you can write this as GUU 1 plus alpha, GVV 1 plus the beta. Then gamma xy square. All this signal processing in time domain, as you look at it, its beauty is important parameter is not really huge. It's a few. Okay? Gamma xy square, very important parameter to evaluate the noise contamination in the system. This is xy. When you put the xy, that's really telling you the major coherence functions. Okay. When you say gamma uv, okay, gamma uv, that's not the major. What's a gamma uv square? What's the value? Say 1. Very clear. That's a pure input signal, pure output signal. So when you take the you know, get the coherence function. That's the one. Perfect, which means no noise contamination in the system. So here's a gamma xy square. And gamma xy square, in the vibration you have done that. And I hope Higyu tapped the bars to introduce noise in there. And even if not, gamma xy square this is a 1. One of the things you could say is when you plot the coherence function, you could dip. You could dip, or you could dip. Did you see this case? You have like 1 or 2 dip. I expect you will see that, because this is really happening. Youngbin, take a look at this. Is always happening right at the resonance, right where the natural frequency of the system is, because it's so-called impedance mismatch, and with giving small excitation, then system responds so really wildly. Small, in that frequency, you just tap it, then it jump around. Okay. All single, right? He will delete this anyway. So when you are working to propose to your yochin, you know, if she likes popular music, not classical, if you keep taking her to concert, she will not be happy. So that's off resonance, what I mean. You have to really, hey, Choro, you listen to me. Any problem? Huh? What? Tell me anything here. What? So resonance, very important. You make your parents very happy, but you don't know how to generate the resonance with your parents. But in your age, I heard this weekend is a parents' weekend, isn't it? Yeah. You going back to parents to do something? No? You should do. I'm going to Seoul this weekend because my mother-in-law is there. She's mid-80s. Yeah, she's still, her health is very good. So we're gonna go up there, then entertain her. She happened to be stepmother. Stepmother is chemo. But they, my father-in-law married her almost whole lifetime, because my mother's real mother, my wife's real mother, passed away when she was 3. So, you know, and it's like real mother-in-law. She's a very good person. So you all go up, not up, you know, go to your parents and at least, you know, maybe have a dinner together or something. That's what I'm going to do. She doesn't need anything else. But once in a while, she likes to go to a Chinese restaurant to have a jjajangmyeon. Really good jjajangmyeon. That's where I'm going. I was there a few times, but that's what she wants. So this weekend, resonate, very easy to resonate. Small input, the small visit, to parents. Parents can be really resonate, so happy, see. Very easy, doesn't cost much. So resonate. Impedance mismatch. Impedance, I don't think you have learned that. So anyway, I'll pass it through. So in this gamma xy square, this is what the measurement related. And as we know the relation with the noise, you can express in that form. GUV, this is complex. G, MN, MN complex. Okay? And addition of complex and complex. How to handle that? And for the definition, GXY is absolute square. So as you look at this case, is slightly different. So we'll talk about this. And the bottom here is all clear. GUU, GVV, all outer spectra is all real. So 1 plus lambda, this is input noise to signal ratio, output noise to signal ratio is all clear. So how to handle that situation? UV, this, not the UV, this complex plus complex to plus complex, this quantity, of course I'm going to reasonably assume that GMN, this is a noise part, noise spectra, is smaller than the rear spectra, okay, cross spectra. That's natural. If it's too much noise, your system is bad. Your system is something wrong. You have to rebuild your system. So first case we're going to work on. First case we're going to work on is GMN is parallel to GUV. Absolute, because this is complex, you have to take absolute. Which means in complex domain, real, imaginary, and GUV is like a vector. Okay? And assume GMN is a parallel, which means it's extending to that point, or subtract that point. Because you can have a plus and minus. So GXY is GUV, GMN absolute, and this can be plus minus. Okay. So then, of course, this angle theta UV theta XY is same. Because this guy is parallel to that guy. Okay? And this here is all parallel. So now back to definition. Always go back to definition. So GMN square is this, right? Because this is gamma MN square, the definitions. Gamma MN square. Remember, this is a parallel case, okay? By looking at that, too high. Let's lower down a little bit. That makes easier. G, Mn, absolute square. divided by GMM over GMM times GNN is gamma MN squared. And GUV is equal to that guy. Gamma UV squared is equal to 1. 1. So GXY absolute square is this. In this case, okay, when GMN and GUV is parallel, and just simply rewrite by taking out the GUV absolute square, taking out. Take them out here. GUV absolute square is GUU times GVV. And so, yes, definition, right? Because gamma UV square is equal to 1. And this is from there. Then GUV is carried down here. This is input noise, output noise ratio. So this is what. So finally you can write the GXY square is equal to GUU GVV 1 plus minus gamma MN square root of the alpha times beta. You will never memorize. When you face the problem to solve, then you will derive. Of course, this next Wednesday, the 18th, is all open book. Just open note. You can bring whatever you need, calculators and all that. You know already taste of my course. How many minutes did you take for a midterm exam? 30 minutes? 1 hour? Shouldn't take more than an hour. Midterm exam. It's all gone from here. Evaporated. I mentioned shouldn't take more than an hour. Maybe you all finish within an hour or so. Okay. This time it may take a little bit more time. Yeah. I'll send you last year's final exam problem set. I heard you guys have all the exam problem set, no? Not mine, every faculty members. It's good to practice. Okay. Back to now, we want to look at gamma xy square. Behavior of gamma xy square. When you have correlated input and output noise, how it's gonna change the behavior, okay? What could be the lowest coherence function we ever can achieve? If its gamma xy square is too low, then you got problem in the system design. So you have to do something else, something different. So here, gamma xy square by definition, just to plug in all here, this cancels out. Then you have a very simple, the final equation for the gamma xy square. Okay, how to achieve the lowest value? How to achieve this lowest value for gamma xy square? That's the idea. How to achieve lowest value? You can change alpha, beta. So I'm going to assume, let's say alpha is equal to the beta because it's unknown. Or you can do by measurements and all that. But to minimize this gamma xy square, you have to subtract from 1, so I can take the minus sign, of course. So I'm going to say gamma mn is equal square is equal to 1. What does it mean? Gamma mn square is equal to 1. It looks like there are a lot of the input and output noises in there. Oh, I'm sorry. Yeah. No. What's the gamma mn? If the gamma xy square is equal to 1, what that means? No noise in there. So here is gamma mn is equal to 1. Mn is equal to 1. It's opposite, isn't it? A lot of noises in there. Can I interpret that way? Anyway, when this guy is the same, assume, and this is equal to minus 1, okay, then if you simplify this equation, so you have gamma xy square is equal to 1 minus alpha, 1 plus alpha square. Then, so we assume like alpha is 0.05. What does it mean, 0.05? The input and output noise is 5%. So here 5%, 10%, because we assume alpha is equal to the beta here, and this is 15, 20, 25%, then of course gamma xy square at the beginning when the noise is very small, then what to expect? You have higher coherence function. But as alpha, in this case it's only wrote alpha, but alpha happened to be the beta here, then if it's a 25%, so what does it mean? Increase the noise, then you see gamma xy square goes down, it's 0.36, approaching to 0, which means lots of noise, contaminations are there. Not a good system to build. So another case is we look at the situation where the GUV absolute is parallel to GMN absolute. Well, that's the one situation. Another situation, critical situation or extreme situation should be this point could be here. So GUV absolute plus GMN absolute this is a GMN, or this could be GMN. So resultant the vector in the complex domain is the point connecting from here to here or here to here. Okay, that's the situation GUV plus GMN absolute. Okay, that's another kind of the extreme situation. We look at when GUV absolute is parallel to GMN absolute. In this case, it's orthogonal each other between this and that. Okay. Then the situation, this is from here to, we just pick up this lower, the portion. So this is theta xy plus the delta theta xy plus this guy. In this case is theta uv minus delta theta, delta theta xy is equal to the theta u. Let's look at here. Theta, this is a final. the final vector in the complex domain. So theta xy is equal to theta uv minus the delta theta xy. Okay? It could be plus and minus, because this is a minus side. If it goes up to connecting from here to here, then that's a plus side. Could be plus and minus. So gxy is equal to guv plus gmn. And now we put the absolute, then two situations could occur. Then this can be, well, simply this is just a vector summation in both the situation, whether when you're adding together it's going to be this vector plus that vector, or this vector plus that vector in a complex domain. When the parallel situation occurs, the resultant vector is from here to here, plus from here to here, or minus from here to here. So in this case, it's orthogonal each other. So this is all you can do for this, but for adding the square, is I think just the plus is appropriate. Then I'm doing the same thing to check out which situation the gamma xy square could give a lower value. So this is a similar way, no difference, in expressing it as a function of gamma mn square alpha beta. Okay? No differences. Then back to definition, then expressing alpha, beta, gamma, mn. So gamma xy square is equal to this. To get the lowest possible value here for gamma xy square, what I can assume is this you can't change anything just to looking at this. If let's say gamma mn is equal to 0, that's the lowest value. So set the 0 and assume alpha is equal to beta because we don't have information. Then gamma xy square happen to be this in this case, but this is a higher than parallel situation because this is a 1, bottom is the same, denominator is the same, but in numerator, this is a 1 for orthogonal situation, and this is 1 minus alpha is there, so this is higher. So this is equal to for the parallel case. So gamma xy square will give the higher the coherence function. So we plot that together. This is when alpha is equal to 5%, 10%, all the way to 25%, gamma xy square varies. So as you look at this solid blue line, is lower than a dashed line, which is case 2, which is orthogonal situations. So overall, this is really telling the situation when alpha, which means noise contamination level changes, how the things varies. So you have a good evaluation approach to say something on that. Okay, I'm going to stop right here, and next we're going to go into feedback system. I mentioned to you Friday is free, so no class after, right? No class after this class. So it's your time to really have a fun from Friday afternoon. But Friday, not afternoon, Friday evening you can have a fun. But, you know, I can do a little bit talk. 154. Feedback. I mentioned to you, feedback, negative feedback system. Negative feedback. Can you, I suggest, think about it. Then maybe some examples if you can find, then talk in the class. Have you thought about it? What does it mean, negative feedback system? To use it, of course, mathematically you can formulate and say a lot of things, but what's the application? What's the situation you have a feedback, negative feedback system? 윤서, negative, 수성, 철우, 영빈. Negative, whoever does control, very familiar. I'm not a control man. So, I look at, of course, internet, not only this time, long time ago too. And there are some good examples, but one thing I can think of is there is a pipeline going. Pipeline is going, there's a valve in there, automatic valve. And when this guy goes, flow in the pipeline, flow goes faster. Okay? If it passes certain threshold, the flow velocity, then the valve opens quickly, then divert the flow in another feedback pipeline. Otherwise, it could blow. So that automatic valve controls the flow velocity, which is really passing here. So then this feedback system, flow system, really release the flow in that direction. Then that will reduce the velocity of the flow, something like that. Or another situation is like some channel goes in there, and there's a kind of some sort of the mass is plugged right into it. Then as the pressure builds in the flow or whatever, then if it's past the threshold, then this plug-in type really opens up, then divert the flow or pressures, then it can reduce the pressure along the channels or things like that. So think of something. So we're going to look at what happens when we have a negative feedback system in there, how we're going to build to evaluate like system parameters or gamma xy square things. Okay, so do something on Parents' Day. Okay, see you.